Welcome everyone to, I guess this is our second colloquium of the new year, and we're still learning how to do this. So forgive us for any audio-visual problems, although we'll try our best to fix them. We're very fortunate to have speaking today Danielle Berg, who's just begun a faculty position at University of Texas at Austin. And Danielle got her PhD in 2013 at the University of Minnesota, working with Evan Skillman. Then she spent a few years as a postdoc working with Don Erb, who many of us know, at the University of Wisconsin-Milwaukee. And then for the last couple of years, she's been a postdoctoral fellow at Ohio State before beginning her faculty position. And she's doing her first term of teaching at UT. And so she's very, very busy. And so we're lucky to have her attention today. And we will, her title today is called Extreme UV Emission, Bridging Galaxy Evolution Across Cosmic Time. And take it away, Danielle.
All right, thank you so much for having me. It's really exciting to be able to talk science today rather than, just helping students solve for the correct significant figures or something like that. So, been teaching a lot, but I wanted to show you some stuff I've been working on recently even. And so I have some preliminary results that I'll share with you today, and not all of it's polished, but I'll be excited to get, reactions and questions and help move it forward. So. Starting just kind of with the big picture of what I do, we'll start simple so everyone is on the same page. I generally study and care about galaxy evolution. And so we can start with the picture that we all know and love, our cosmic timeline, where we have the events that define it. We know about the Big Bang and the cosmic microwave background. And of course, we had this period of dark ages. And it wasn't until the first massive stars and the first galaxies that released copious amounts of high energy ionizing photons that it started to reionize all the neutral hydrogen so that we could start to see the seedlings of galaxy formation. So once we get a little bit further, a couple 100 million years later, we start to get our very deepest picture of what galaxies look like, looking back in time with the Hubble Ultra Deep Field. And we see that at redshifts of 4 to 5 to 6, we see kind of soupy, blobby, various colors of things that are starting to form, but really simplistic structures. And they continue to evolve through the peak of star formation rate and all the way to this beautiful complex picture that we see today from giant ellipticals and spiral galaxies and irregulars. And so what I really work on is using the bright ionized gas around stars to try to understand how we can put all these puzzle pieces together over cosmic time and understand how we got here today. And of course, the big challenge of that is that when we look back in time, we're looking at different galaxies and different snapshots throughout cosmic time. So it's really hard to string and piece all these pieces of information together. And so the big piece of information that I use to help trace this is a really simplistic idea. If we just trace the massive stars within a galaxy, we are able to see that we can start first with primordial gas. And when the first stars form, they're going to produce the first heavy elements and blow them into that gas when they die. The next generations of stars that form will start metal enriched, produce more metals, put them back into the gas again when they die. So that we get this cyclic recycling process where metallicity builds up over time with consecutive bursts of star formation. And it also is this productivity or progression marker of evolution through a galaxy. Of course, the picture is more complicated than that. So with star formation comes these metals, but they don't necessarily have to stay in the galaxy. They can be recycled, or they can be completely blown out of the galaxy. We can also accrete new primordial gas onto the galaxy that can dilute things and trigger new star formation. And so there's a lot of competing processes that change the overall chemical composition of galaxies that we look at. And as we want to start building these pictures and looking more distant, of course, we come into a different challenge. We've started to do really wonderful things with cosmological simulations. But of course, these are very computationally intensive. And so when we want to do the universe, we do really large scales, but we don't necessarily get the details all the way down to redshift 0. If we do that, we usually focus on just a couple of galaxies. And whereas with our images, and spectroscopy, the best ones that we have are in our backyard. The things that are brightest are, most spatially resolved, things that are easy to look at. And so as we get further away, it becomes really hard to get good enough observations to match the simulations. As you can see from just an example image of a galaxy with the Hubble Space Telescope from about redshift 2, that's really challenging to match, but really excited, looking forward to the next generation of telescopes. Hopefully the TMT will happen for you folks. And then I'm excited to be at UT Austin, where we're going to have access to the GMT. And we'll be able to take something like this galaxy on the left and actually start to be able to resolve different strings of gas and clumps of stars and things like that, and start to actually be able to match predictions from these simulations to our observations. So the big questions that I'm excited to work on and continue to answer are, really structured around these three big topics of the first galaxies, what their properties were, and how they evolved to what we see today. The first two questions on here really have to do with the early universe. And to fully answer these questions, they're going to require James Webb or the next generation of telescopes to get the details that we need on these very distant galaxies. The third question, however, though, is putting together all the multi-epoch data that we have and forming this fuller picture. And so we have a ton of information already that we can use, and future and ongoing projects that can give us insight to understand this. So I like to start really simple, just in case other people don't work on what I work on. So the really simplistic picture, I don't know where the background galaxy went, but an H2 region is where you have a burst of star formation, and it ionizes the gas around it, so that you now have H+, you have hydrogen ionized in the center. But closer in, you're going to have higher ionization species where you have more photons. So you'll get things like doubly ionized oxygen and sulfur, neon, and argon. And then farther out, where you have less ionizing photons, you'll get singly ionized species. Real H2 regions are obviously more complicated than this, but we can think about a simple 2 or 3 zone onion to help understand what we're looking at. That was the H2 region you were supposed to see on the first slide. So when we then put a spectrograph on one of these bright star forming regions, let's say a long slit in the optical or a fiber in the optical, we get a lot of really wonderful information. We get recombination lines that are really strong from hydrogen and helium, like the Balmer series. We also get really strong collisionally excited lines from species like oxygen 2, oxygen 3, nitrogen 2, sulfur 2. There's things like nebular continuum and underlying stellar continuum that also tells us pieces. These emission lines can be really powerful. And with the collisionally excited lines, one of the things that you'll notice is that the intensity or brightness of that line depends on, the abundance of those atoms that are there, but it also exponentially depends on the temperature. It's very sensitive to that. And so this weakness is also its strength. So if we are able to measure 2 emission lines from the same ionic species, that means we can take a ratio and not worry about the abundance of that element anymore. So if we take 2 oxygen 3 lines that come from different energy levels so that they have different temperature sensitivities, we can solve for that temperature within the gas. And once we know that, we're able to solve for the rest of the ionic abundances. And for something like oxygen, we can just add up all the ionic species that we see to get the total abundance within the gas. Oxygen is the easiest one to observe and the most abundant by mass. And so this is what we typically use in nebular regions. Now, I love to do those type of direct abundance measurements with really deep spectra, but most of the time, especially with distant galaxies, that's hard to do. And that's because this temperature sensitive 4363 line that I've blown up here is actually really, really faint. It's usually about 1/100th maybe of the strength of H beta when you have a really nice detection. So instead, people use, these beautiful strong lines like O2, H beta, and O3, and then they'll take different combinations of them, relate them to metallicity to get these empirical calibrations. And while these can be messy and they have other dependencies, the power of them is that they allow us to determine what abundances are for an entire population of galaxies. Probably the most famous example that people know of is using those strong line metallicities to create the mass metallicity relationship from Tremonti 2004. This was from the Sloan Digital Sky Survey, using hundreds of thousands of galaxies where you have metallicity on the x-axis and stellar mass on the y-axis. And you get this beautiful trend of building up abundance with more stellar mass. And so this is kind of seen as, an evolutionary trend here. Now, that plot I just showed you is equivalent to this pink one up here in the corner. And that's because the brightest galaxies are the most massive. So, solar masses from 10 to the 9th to 10 to the 11th, that's the typical mass metallicity relationship that people are often comparing. But what about all the smaller galaxies? So in 2012, I did a consensus of the local volume, finding as many, these low mass galaxies as we could, get direct abundances for, good distances to get masses, and found this beautiful tight trend. It's not upsetting that it's offset so much because, again, this pink one is more of a calibration, empirical calibration, whereas the gray is a direct abundance. But what we see is that this trend extends all the way down to the lowest mass building blocks that we observe. And of course, as I mentioned earlier, there's all these processes that shape this. So it's really informative to study the mass metallicity relationship. With star formation, of course, we build up the stellar mass and we get more oxygen abundance out. So we go upwards along that diagonal. We can also have pristine inflows that can dilute our oxygen abundance while also triggering then additional star formation. We can also have enriched outflows. And so this could be that you stay at your exact same stellar mass, but you eject the metals that you just created and stay at the same oxygen abundance. And then empirically, we've also observed evolution within the mass metallicity relationship using strong line calibrators as we look out to more distant galaxies at redshifts 2 to 3. Of course, this depends on what calibration you use if you want to understand the absolute evolution of the mass metallicity relationship, but this is exciting. So these low mass galaxies that I really like to study, not only are they useful for extending the mass metallicity relationship, but they offer this window into this really unique chemically young laboratory where we can start to understand chemical enrichment pathways and put really nice constraints on lots of our simulations. So I've been working in this very low mass, very low luminosity regime. And one of the things that's interesting is people have wondered if environment affects how these galaxies evolve. And so again, we have my gray trend from those 2012 LVL galaxies, local volume galaxies. And what you see is that there is a whole bunch of points on here that are from a study by Pustelnik, who looked at galaxies within a void as opposed to a normal field, and found that on average that they were offset by about 0.3 dex from these normal galaxies. And so there was this theory perhaps that things actually just evolve slower within these voids. In a recent paper that came out this year, I worked with Christy McQuinn, who is now a faculty member at Rutgers. And we went back into this Pustelnik void data and we took only the very best spectra, so took things that had direct abundances. And what we found is that when we only use the direct abundances, these relationships now agree within the uncertainties. This is a little bit challenging because some of these are just really faint. And so it could be that we just don't have deep enough spectroscopy to understand the ones that are true outliers and why they evolve more slowly in the void. But it also could be that they were just contaminated with not the best data. So they seem to agree now. Now, we can use these trends to compare individual very metal poor galaxies to try to understand what we're seeing. So one of the things that's really interesting is that on the luminosity metallicity relationship on the left, we see lots of these classically extremely metal poor galaxies where, you know, you're about lower than about 5% solar here. So there's, you know, famous galaxies within here of 1 Zwicky 18, SBS 0335, all your favorites that way. They seem to lie really far off the luminosity metallicity relationship. And the thought here is that they are being triggered by a recent inflow of pristine gas that is really triggering, you know, keeping their metallicities low, but triggering this luminous burst of star formation. They then, as you can see, once we go to the right-hand side on the mass metallicity relationship, they kind of slide over and agree more with that relationship. And so they appear pretty normal that way and just appear to be kind of more luminous than you might expect. Another recent galaxy that's been studied is Leo P. Leo P is really, I'm going to have a little bit more to say about Leo P. It's a really interesting galaxy, but it's currently the only extremely metal poor galaxy we know of that sits on both the mass metallicity and the luminosity metallicity relationship. So we think that this galaxy is actually just following normal secular evolution. And then another recent discovery, Liancino, agrees within the uncertainties with the mass metallicity relationship, but is offset from the luminosity metallicity relationship. So again, there might be some sort of increased star formation that's happening here, but based off of radio observations and things like that, it doesn't appear that there's you know, any disturbed H1 profile for Liancino, that it's having the same sort of infall that these other galaxies have. So that's really interesting. Now, after oxygen, nitrogen is really exciting to look at. Nitrogen happens on different timescales for its production than oxygen because it's produced more so in intermediate mass stars. And so you get this delayed production compared to oxygen. And then there's also a primary and secondary mechanism through which it's produced. So if you all recall your CNO cycle, we can have just normal primary nitrogen return where we kind of set this minimum level. Primary means we only depend on the initial hydrogen and helium that's within your star, and it just builds up through normal fusion. But you can also then start to have some nitrogen that seeds the CNO cycle that goes into this cycle here once you have a little bit of metals built up. And then you can start to get this secondary trend where you start to get nitrogen that is dredged up to the surface of stars and kicked out at this bottleneck step here. That's the slowest one. So as you start to get more nitrogen that's kicked out from the CNO cycle, we get this additional secondary contribution. And so we get this classical N to O shape with oxygen abundance. So we wanted to, you know, study how the most metal poor galaxies are affected by this nitrogen to oxygen cycle. And so this is Leo P. It has one bright O star at the center. It's kind of this beautiful creation. It's the only single star H2 region that we know of. And we have some beautiful contours of H alpha flux. This is from Evans 2019 from their MUSE data sitting on top of a beautiful Hubble image here. And there is, if you look at their oxygen 3 footprint from that same paper, it's just this nice tiny little H2 region that sits right around that central star. And so even though Leo P is really close at only about 1.7 megaparsecs away, we can still try to get really close on the center of the H2 region and try to understand its abundances. So we threw a Hubble COS aperture on there to get some UV spectra. And these are some preliminary findings that in the UV, we got really beautiful oxygen 3 emission lines. But what was really surprising to us is that we got this nitrogen 3 around 1750 emission lines that I do a lot of UV spectroscopy and I really don't see very often. This is really, really rare and pretty high ionization for nitrogen. And so really interestingly, if we go back to this N to O versus over H plot, where we have a bunch of dwarfs down at low metallicity and spiral galaxy H2 regions at higher metallicity. We can see that from the optical spectra of LEOP, from low ionization nitrogen to oxygen, it was a little bit high compared to what we might expect in N/O. It's at about minus 1.35, but it's within the dispersion we see for dwarf galaxies. The new abundance, preliminary abundance that comes from the UV data from the high ionization zone puts it much higher. And that makes a little bit of sense of why we're even seeing that nitrogen line at such low metallicity. And so this is really interesting, and we don't yet know what is causing this nitrogen enrichment. Wolf-R A stars are super rare at very low metallicity, and we also don't really see any winds from LEOP at all. So we aren't sure where this nitrogen enrichment is coming from. Another trend that I've been studying with dwarf galaxies that I study is looking at how carbon and nitrogen relate as a function of oxygen abundance. And remember that we saw that nitrogen increased as a function of oxygen abundance, and we see similar trends with carbon. So the thought was perhaps there's something interesting about their production mechanisms, even though we don't know them to be linked, that causes them to act in a similar way. And so we do see a flat trend in carbon and nitrogen. There's a lot of scatter, but it is relatively flat. So our next line of study that we hope to be getting is that we're going to try to get the carbon abundance from LEOP. And that'll be a really good test. If the carbon is also really high, that would be a really good indicator that carbon and nitrogen seem to be linked. So that's, stay tuned for that. We're hoping to test that soon. All right, phase 2 of my talk is all about why I love the rest frame ultraviolet, and that will lead into my Large Hubble program at the end. So the rest frame ultraviolet is, in my opinion, the wave of the future, because it's the one spectral regime that we can access for all galaxies. So it's challenging in the nearby universe because we have to go into space, use the Hubble Space Telescope to get good access to this UV, but we've been doing that for years, and hopefully we'll continue to for a few more and continue to get really good data. But as we go a little bit further, there are many people at Caltech that have taken advantage of the beautiful window that opens up in the observed optical frame. As the UV shifts there for redshift 2 to 3 galaxies, you can start to observe them from the ground and do that with really nice big telescopes that we have. And then, of course, once you get out to really distant galaxies and we want to start studying the epoch of reionization, the bright UV lines are going to be the easiest ones to access. You can still get the optical lines, in the mid-infrared and things like that, but this will be the easiest window to get. So if you're not super familiar with looking at UV spectra, let's orient ourselves. So the strongest emission when it exists is the Lyman alpha. And Lyman alpha is really important because it's our best tracer of Lyman continuum, and Lyman alpha resonantly scatters. And so it has to be able to get through that same gas that would be absorbing Lyman continuum or ionizing photons. So of course, just to give you the really simplistic, little fun diagram there, you have to be able to, the first one was, a complete ionization or escape. And then the second one was just being excited to that second level, which is where you get Lyman alpha. So the hydrogen is really easily going to absorb and rescatter that. And so you want to be able to get past that. There are two ways that we think in a simplistic model that Lyman alpha might escape. On the left, in an ionization bound nebula, we might have previously blown out holes with a previous supernova or something of that nature. And once you have these holes of relatively low opacity, then you can start to get photons that leak through there. The other one on the right-hand side might be that you have a density bounded nebula where you're just running out of enough gas to fully absorb it. And so then light can start to leak out that way. And the cloud example of this is always really, really nice, where holes are punched in the clouds and you get beams of light coming through compared to a more hazy day. Now, Lyman alpha can really tell us a lot about what we're looking at. And so this is this really nice figure that Don Erb had it in a Nature paper a few years ago. And of course, I had to animate it. So you can imagine we have a nice central burst of star formation, and you have a neutral gas cloud and an ionized outflow that's driving everything out. So when your central starburst releases photons, you're going to see that it's going to absorb those photons along the line of sight. But if it's backscattered off of this cloud, they will now be redshifted and can travel towards us. And so then we get this Lyman alpha profile that is redshifted like this. Again, simplistic model, but it helps. Now it's also really fun. We see a lot of these double peaked Lyman alpha emitters. And this can happen when you actually get some photons that are blue shifted that can travel through the front of your cloud. But you still might also get these backscattered redshifted photons that can then travel towards us. And so we'll get photons not at the center, but just at the blue and redshift peaks of our line emission. All right, after Lyman alpha, a lot of other lines that I think are a lot of fun can be the next strongest ones. So you can get these oxygen 3 emission lines, and these are the UV counterpart to the oxygen 4363 in the optical, the temperature sensitive line. So these lines are also temperature sensitive. We get this carbon 3 doublet, which is a really nice density dependent ratio. You sometimes get these very high ionization species in certain galaxies. And you get silicon 3 emission when you don't have a lot of dust and you have enough metals there to get it. So that's also a really nice set of lines to look at. And then of course, besides the Lyman alpha, the emission lines, and ISM absorption lines, we also have a ton of stellar features within the UV. So there are some of these stellar features that are very sensitive to the metallicity. So you can see if we hold an age constant, but we evolve the metallicity of these models of carbon 4 and silicon 4, you can really see how the profiles change as a function of metallicity. And then sometimes the same lines or other lines can also be sensitive to the age of your stellar population. So now we're holding metallicity constant and aging our models from 10 to the 6th to 10 to the 7th. Years, and you can again see how drastically these profiles change. So they're really good at constraining what our stellar population is that's doing the ionization right now. All right, so why am I so excited about the emission lines? Well, we're all familiar with a lot of these diagrams of the challenges at high redshifts. So the first problem, of course, is that galaxies in the epoch of reionization are going to be really tough to observe, especially their Lyman alpha, due to the increasing opacity of the intergalactic medium. So this is, fractional throughput that you're going to get from your galaxy. And you can see that it really is going to drop off right after Lyman alpha. And as we go down in redshift, we eventually don't get any photons that can come to us blueward of Lyman alpha. There's also this evidence that the luminosity function is evolving such that it's more and more dominated by these low luminosity galaxies. And so we think that these kind of more interesting, extreme, dwarfy galaxies are going to be really important contributors to reionization. But of course, they're fainter, and that makes them harder to observe. Fortunately, people have been staring at these really distant galaxies with very long observations are finding that you do see some of these really bright emission lines, and especially some very high ionization lines like carbon 4, helium 2, high ionization lines, oxygen 3, moderate carbon 3. And so this is very promising that we'll be able to detect these really bright lines with James Webb and ELTs. These UV emission lines are also hopefully going to be important in diagnosing what we're looking at. And so if you're familiar with the optical BPT diagram, where we differentiate between AGN and star-forming galaxies, this is what is kind of thought of as the UV BPT diagram, where we can use carbon 3 over helium 2 and carbon 4 over helium 2. These are theoretical models to be able to separate AGN in gray from star formation in green. There have challenges to all of these lines, and this is not fully worked out yet, but it is exciting and promising. And then, of course, we've seen that emission line strengths seem to be related to the number of ionizing photons that are produced. We can look at this in the UV and optical. And so this is also really promising that we can look for these really strong emitters to try to find the ones that are producing and hopefully also leaking some of the highest fractions of photons. And then finally, the star formation rate density peaks at redshift 2. So of course, this is an excellent place to look for the diversity of galaxies that might represent some things we see in the epoch of reionization. But I'm also going to argue that redshift 0 is a great place to do that. All right, so in the local universe, it is always a little bit scary to use the term epoch of reionization analogs because we don't actually know what the galaxy populations in the epoch of reionization are exactly like. All we know are some of these basic properties that we can try to match in the local universe. So when I say analog, I use that term loosely, but we can go after some of these high star formation, compact, metal poor, high beta slopes galaxies to look at them and try to find conditions that are similar to what we think is happening in the epoch of reionization. So I've been studying these types of galaxies in the ultraviolet with the cosmic origin spectrograph on Hubble. This is what they look like in Sloan, in the optical. And then here is a couple of just small pictures of what they look like in the ultraviolet, in the near UV. You can see now that most of them have really compact star forming clusters. Sometimes they have just one or two that's really dominating these small galaxies. And because they're nearby, how small are they? Well, the COS aperture is about 2.5 arc seconds. And so for one of these galaxies close to a redshift of about 0.01, we get that they're all contained within about half a kiloparsec. So they're really small. This is what low resolution spectra with Hubble Space Telescope looks like. This is what good spectra looks like. It's really hard to do good UV work. And this work originally set out to measure a bunch of carbon and oxygen abundances, and this did this successfully. So that's all those lines that you see there. But what was really exciting was that we found a whole bunch of carbon-4 emission and helium-2 emission, these very high ionization lines that we weren't necessarily expecting. Now, the reason why that's really exciting is that if we look at spectral energy distributions versus photon energy, where gray is some AGN, and then we have two different star-forming galaxy stellar populations in blue and orange, different metallicities, you can see that carbon-4 happens right around 47, 48 electron volts. And so you can just barely get that with a low metallicity galaxy. And then helium-2 is actually recombination from helium-3 happening up at about 54 electron volts. And so our stellar models don't reach that. We don't know how to produce it. The other thing that's really interesting is that we typically see for most galaxies, carbon-4 stellar profiles or an ISM absorption. So this is an example profile of a lensed galaxy from the Megasaur survey of its carbon-4 lines. And it's a combination profile, like I mentioned. So the first thing you do is you fit the overall stellar population, and then you subtract it, and you're left with these really deep absorption lines. This is really common in the interstellar medium. And so you can compare it to its theoretical ratio of its oscillator strengths, and you see that these lines are saturated. That's how much carbon-4 is there to do the absorbing. So when you see these really big pure emission, that's really unique. And so we took two of these galaxies from the sample, one that happens to have the largest helium-2 equivalent width in the local universe, and one that happens to have the largest carbon-4 equivalent width in the local universe, and got better spectra. So you can see going from the low resolution to the high resolution spectra, these are much more beautiful. And we can zoom in on these profiles. So helium-2, again, remember, is very high ionization. We don't know how stars would form it. And so a lot of times people are looking for broader helium-2 profiles to see if they're from, some sort of Wolf-Rayet stars or other energetic, occurrence like that. But here I'm comparing in green to the oxygen-3 nebular line. And you see the helium-2 is just as narrow. So it seems to be also nebular in origin. If we zoom in on the carbon-4 lines, the really surprising thing that we found was that the carbon-4 lines are much broader. This shouldn't be a surprise because carbon-4, like Lyman alpha, is resonant. So it will scatter in high ionization carbon-4 gas. And so treating it like Lyman alpha, we decided to fit it with a double peaked profile. So in J10, 4457, the stronger line is 1548. And so I fit this line with a double Gaussian, and then I use the emissivity ratio to predict the 1550 doublet. And you see it does a beautiful job. So this says that this is probably, pure emission going on there. And this is really, really exciting because that means there's very low high ionization gas along the line of sight, and very high energy photons could be escaping through this gas. Very high energy photons, the ones that, ionize helium-2 to helium-3, they have very low cross sections with neutral hydrogen. So they don't really care about that gas so much. They care about this high ionization gas. And so the idea is that this galaxy could be leaking very high energy photons. J14 has a similar story, but when I predict 1550, it's a little bit lower. So this means that there is probably some absorption going on in this galaxy. But again, to get this kind of emission, this still means that we have very low column density of high ionization gas along the line of sight. So this is really fun to me because if we look at J10, again, carbon-4 double peaked resonant emission, it has a damped Lyman alpha profile. And so this is fun because, different ions are sensitive to different ionization phases of gas. So we can get different energies out. And I will say more about this at the very end. Now we see these emission lines, in these beautiful redshift 2 and 3 galaxies that we get from the ground as well. So one of my favorite ones is this lens galaxy that I worked on with Don Erb, SL2S0217. And in this work, our main goal was how can we reproduce these emission lines? And so the punchline is I did a whole bunch of photonization modeling. I did combination modeling with binary stars from BPAS. I did combination modeling with AGN models and shocks as well. And no combination of those models could simultaneously reproduce all of these emission lines. If you crank up your AGN or your shocks, you can get helium-2, but it throws off all your other line ratios. And so we still do not know how to produce this suite of emission lines. There's a lot of interest in this. People are still duking it out. Is it very massive stars, strip stars, high mass X-ray binaries? We're looking at some Chandra data at some of these dwarf galaxies to look for X-rays and very high mass X-ray binaries, but the verdict is still out. So back to our dwarf galaxies, we recently got, oh yes, I showed you these UV spectra already. And so I wanted to show you that there were some other very high ionization emission lines. We have oxygen-4, really faint oxygen-4 emission. We also have some silicon-4 emission. That's really exciting in these two galaxies. And then we recently got some large binocular telescope MOD spectra and found a bunch of other very high ionization emission lines. We've got some very weak neon 5, neon 3, and this is really exciting to me. And I'm hoping to do some more studies on this in the future. But this is the first galaxy in which I have detected iron 2, iron 3, iron 4, and iron 5 all in emission. So people don't usually do nebular iron abundances because they heavily deplete and because the ionization correction factors are terrible. But when you observe all the relevant species, you can do the abundances. So this is really phenomenal to get iron 5 emission like this. We also have the argon 4 emission lines. And so we do a high, ionization density. And the punchline, I have sent this paper to collaborators, so it'll be out soon, but it's not quite out yet. So we're still trying to figure it all out. But the punchline is, I think sulfur has a bad ionization correction, but if sulfur was corrected, then oxygen, argon, neon, and sulfur, all of the alpha elements for each of these two galaxies would have similar abundances, about 5% for J10, and around 9% for J14. But nitrogen, carbon, and iron are significantly depleted relative to that. So you're looking at 2% for both of these galaxies. And of course, like I mentioned, iron can deplete, but for these two galaxies, we've measured, the dust with the Balmer lines, with the helium-2 lines, with the stellar continuum, and we get really, 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 really low extinction. And then also nitrogen does not deplete. And so it's very surprising to get these extremely low, relatively deficient abundances for nitrogen, carbon, and iron. I'm hoping to talk to Chuck about this at some point because, we think that having these relatively alpha enhanced relative to iron could be one of the ways that we get harder radiation fields from stars and get these emission lines that we see. So I just wanted to give a shout out to my graduate student, Grace, who has been doing the stellar continuum fits on these galaxies. They were zoomed way in now on those same spectra, and their absorption features from the stellar spectra are super weak because these are young and they are metal poor. But she's then using those stellar fits, putting them into the photonization models to try to fully model the spectra that we're seeing. The takeaway is that in her photonization models on top, we have a couple of different metallicities in the different colors. And then you have ionization parameter on the x-axis, and then some different ionization species on the y. So we have nitrogen 2, oxygen 2, sulfur 3, and argon 3 lines that we observe. And then all of our dwarf galaxies, agree pretty well within these models. That's the takeaway. Don't stare at it too long. However, all of our high ionization species, ordered from low to high, oxygen 3, argon 4, neon 3, and helium 2, we start to lie progressively outside of the models. They can't reproduce it. And so this is a combination of perhaps not having the chemical composition exactly correct, like the example we just saw from J10 and J14, but also the fact that this isn't being pulled through into our models either. And so that's the next step, is to see how much energy we're actually missing, how we could reproduce these, and if this abundance problem would solve it. All right, some of my slides are supposed to be skipped. I don't know why they're not. We're gonna skip them because I wanna finish up and tell you about Classy. So I apologize about this. Yes, so summary of those galaxies. The rest frame UV is amazing. We've got stars, we've got Lyman alpha, we've got emission lines, we've got ISM absorption lines. We can sometimes get these really strong nebular emission lines that tell us about how hard our radiation fields are. We also have other resonant lines that can tell us about the potential for high energy photon escape. And then we're also working on all these other emission lines to be diagnostic for the ultraviolet in preparation for James Webb and the ELTs. But this all depends on us calibrating the UV as well as we've been calibrating the optical. So that was motivation for a large Hubble program that I am leading. In the past, the Hubble Space Telescope has studied with UV spectra kind of one section at a time. So certain investigators would use this part of the UV spectrum to maybe study stellar winds or Lyman alpha, but then they wouldn't study any other part of it. It was all hodgepodge. So then a different set of investigators would get a set of galaxies and study this part of the UV to get nebular emission lines and maybe some different stellar winds. And then very few of us, but I would always do this, would get this part of the spectrum and try to study some other physics that happened here. And we didn't have a uniform set of galaxies that covered the full UV. And so this led to a proposal of the Cost Legacy Archive Spectroscopic Survey. And what our chief goal is to take everything in the archive, add what is missing, and unify it. So we have really good UV coverage. All these galaxies already have optical coverage. And we can start to really understand the stellar properties, the gas properties, everything that's happening, and create these templates and this atlas that will be applicable to galaxies from redshift 0 to forever. And we're going deep and we're going high resolution. So we're going to get a whole bunch of even better lines that will allow us to do anything you want. So the Hubble Spectral Legacy Archive, before we started Classy, only had 2 galaxies that met our signal to noise and resolution, spectral resolution criteria in this full wavelength coverage, only 2. So the sample is now 45. And it's going to allow, you know, all the science things that I've been talking about that we've been doing for these individual galaxies. We're going to have a whole set and be able to link all these different science pieces. How do you know that we have galaxies that are going to be right for whatever you want to match? Well, we tried to really spread them out in terms of properties. So we have a good range in terms of stellar mass and star formation, oxygen abundance, specific star formation rate, ionization as characterized by the oxygen 3 to oxygen 2 ratio. And then we also tried to span density, since there is some evidence that perhaps higher redshift galaxies have higher nebular densities. So the punchline is that our survey is now 95% complete. We're just waiting for the final data to come in. It's super exciting. This is just to give you an idea of somewhat what some of these acquisition images look like. Most of our clusters are very, very compact. And so we get, on average, more than 90% of the near UV light that goes through the COS aperture. But unfortunately, we still get spatial profiles that are slightly extended because they're not point sources. And so we've been using these spatial profiles to model the line spread functions for each galaxy. We're trying to do really careful analysis here. And then we're doing really careful co-adding of the spectra. So this is just an example where you can see there's different colors here because there are different gradings that we're adding together. So the Classy data set in total has 93 archival data sets, or 177 orbits of observations. And then we have 58 new data sets from 135 orbits. And so the challenge is, you know, combining these multi-visit, multi-grading spectra that are co-added into final spectral templates that you can use. So we've been carefully doing that. To give you an example of what this looks like when we get done, up top, again, for an example galaxy, you have in green is one of our high resolution bind spectra. And then in this middle panel here, it's now our moderate resolution spectra, and we're taking signal to noise measurements at lots of different places in the continuum. And we have lots of lines that are marked. You can see there's lots of good stuff happening here. And then we also have signal to noise ratios. Our goal was for stellar features on the bluer end here was to be above 5. Sometimes we have a lot more. In the red end, we didn't focus so much on getting high signal to noise there as we were going after just the emission lines that were there. And so the final output will be lots of flavors. We'll have a very high resolution that's really just kind of the G130M only. We have a high resolution that combines 2 sets of the gradings, medium resolution that kind of covers that full wavelength set. And then some of our galaxies also have additional low resolution data, and we want to use everything we can. And so you'll kind of be able to choose whichever one you want based off of your science goals. The average for our sample so far at 1135 angstroms, so kind of close to Lyman alpha, is the average signal to noise in the continuum is 5.6 and the median is 4.7. So it's really good, right where we wanted it to be. I just want to mention that this is a ridiculous list, but this is a Treasury survey. And so we're putting out a ton of products to the community. So stay alert for these. We're going to be giving you everything you could possibly want to use in an easily accessible format. We're going to have, tutorials and Jupyter notebooks and all that kind of stuff. So lots of high-level science products that will be coming out soon. Here's an example of some of our nicest emission line spectra. So just to give you some preliminary notes on what these look like. So far, we have 24 helium-2 emitters. 19 of them are just narrow emitters. 5 of them have an additional broad component, so we can look for some stellar contributions to that. We have 12 carbon-4 emitters, 8 are pure emitters, and another therefore we'll have to model and subtract the P Cygni profile out. There are going to be 25 galaxies from this sample that we'll be able to do new C to O measurements for, 27 that we'll be able to do carbon densities from, which is a notorious challenge. We tend to measure much higher densities from carbon-3, so looking forward to that. And 2 that we're able to do silicon-3 densities. And then these need to be looked at further, but we have potentially 7 nitrogen-4 emitters, 7 nitrogen-3 emitters. These are not the same galaxies. And then 15 that seem to have some weak sulfur-4 emission. So really exciting to be able to model all of those. And then this is, just preliminary snapshot of what all our Lyman alpha profiles look like. Because we're using archival data, these aren't all new, but these are the new ones. We have 27 new Lyman alpha spectra that had never been observed before. And of course, there are a bunch of really cool emission in some of these. So of this, I classify 24 as strong Lyman alpha emitters, so they have really large equivalent widths and not much damping at all. There's another 7 that have weak emission or are sitting on top of a large damped profile. And of these nice, strong Lyman alpha emitters, or 16 of these are new from Classy. So this is really exciting to look at. So coming back to all of these resonant lines, I've been really fascinated with them. And so from Classy, we're getting a lot of really good data where we'll be able to look at multiple species that are resonantly scattered. So silicon-4 is another one. So this is a galaxy from Anjascot that found double peaked silicon-4. So that's really interesting. And in particular, it's going to be really fun to compare that with all these strong high ionization emission lines and the various Lyman alpha profiles that we get within Classy. So again, my 2 favorite dwarf galaxies are within the Classy sample. And so just recently, we followed up, motivated by these interesting Lyman alpha profiles we got from them, one that has a really strong double peaked Lyman alpha emission, and the other one that has a really strong damped profile and just a tiny bit of emission. In fact, I showed you this profile earlier of a low resolution spectrum, and we didn't think there was any emission there. And so we just recently got some DTT time on the Greenbank telescope to look at their H1. Ignore the line centers, only an approximate redshift was used, but basically we got these really nice, strong, narrow line detections, and we're able to calculate mass in H1. And so even though we have escaping Lyman alpha happening here, we still have really large neutral hydrogen around these galaxies. So this is perhaps, I'm hoping that this might be evidence for some holes, and we hope to eventually get higher resolution data as we continue to build this information in this case. So I will leave you with that. I am really excited about Classy and the templates that will come. And I think that it's really going to help us be able to, this power of the far UV, be able to bridge our near and far universes to understand galaxy evolution. Thank you.
Thanks, Danielle. Thank you very much. I think the way that we're going to try to do questions, I think you should have a little thing that allows you to raise your hand, and then we can unmute you. Yes, I see that there's one. But Monsi or someone else on the committee, if you could help me, my cursor always disappears when I do Zoom, and so I don't have control over it.
Sure.
If someone...
Yeah, I can help check. But first one, I think, is Ranga Ramchari.
Hey, I would like to know, we've looked a little bit about the helium-2 to H-beta ratios in local starburst galaxies in a similar mass range that you looked at. And we found that at least if we change the slope of the IMF, we get a pretty good fit to the ratios that we see. So you mentioned that you have some problem reproducing the high ionization lines. Have you looked into changing the IMF to see if you can fit all the lines? I mean, we found typical values of dn, dm going as m to the minus 1 to 1.6 would be adequate to fit those, for at least helium-2. I haven't looked at the other ones.
So the only models that I used were the ones that were available, you know, within BPAS. So I went as extreme as BPAS went. But of course, I mean, of course, this is a long-standing challenge and problem, and I don't do it justice. There are decades of research on helium-2 and many people that should be recognized, so I apologize. But one of the other cases that is really challenging or interesting is into local galaxies, you know, like SBS 0335 has been studied in great detail, where the stars have been mapped, the Wolf-Rayet stars have been mapped, the soft and hard X-rays have been mapped spatially in that galaxy, and they still have troubles matching it up and understanding where the helium-2 is coming from. So at least, you know, in that case, that's a particular example where they know what all the stars are and they still aren't able to reproduce the helium-2, just from an energy contribution standpoint.
Okay, thanks.
It would be really interesting if we were, you know, if we had a, you know, a heavy massive star in these dwarf galaxies are like, you know, 10 to the 7th solar masses. They're tiny, 10 to the 6.5. So that would be exciting if it were true.
So let's see, it looks like, I think Evan had his hand up, maybe just before Lynn did.
For some reason, I didn't have a hand. I only had a thumbs up, so I gave a thumbs up for a very lucid talk. I had just something to say about the mass-metallicity relation. You attributed the break in the mass-metallicity relation between the nebular line abundances and the aurora line abundances to just a calibration issue. I wanted to point out that for stellar metallicities, we have a similar issue. Nisha Lita-Chalowit was a PhD graduate student from Caltech in 2019. And as part of her dissertation, she found that the mass metallicity relation measured in stars for low mass galaxies with individual stars versus high mass galaxies from integrated light also had a break in the exact same direction. And it looks the slope, it looks similarly different to the two slopes in your relation, and also the break in normalization also looks similarly different. I'm not saying that this is actually a real phenomenon, but it's just amazingly coincidental that if we can chalk them both up to systematic differences in technique, and these two systematic differences work in the exact same way.
That's really interesting. I will have to look at that. Of course, strong lines vary hugely depending on which method you choose. So I guess I was just allowing it the leniency. But yeah, I'd be grateful if you would send that my way, Evan.
Sure, absolutely. It's even at the break is even at the same stellar mass that you were showing in your plot.
That seems remarkably coincident.
It is, it does.
I think Lynn had her hand up. It's the one I see anyway. Lynn?
Can you hear me?
Yes.
Ah, good. Okay, great. So sorry about that. I was on mute. I work on Z of 10 to the minus 7 or so this could be a naive question, but I was also curious about the helium-2 and carbon-4 lines. And so there's no possibility that you have, you know, slightly evolved stars, because, you know, Wolf-Rayet stars have these kinds of lines, and that's of course also nebular, you know, circumstellar, you know, part of it's generated there. So, or the scattering anyway. Is that a possibility for these objects, or you're saying it's all lower mass?
Yeah, so I guess the main argument against Wolf-Rayet stars is we don't see them at, you know, 5 to 7% solar. They typically don't form in that metallicity range. The other thing that I didn't show you is there are no winds in these galaxies. It could be just, it's possible that it was, you know, it was a rare formation of Wolf-Rayet star and we are just post the Wolf-Rayet, so we're not seeing the winds anymore. That's possible. But we're certainly not in a Wolf-Rayet phase right now. the ISM absorption lines are incredibly narrow and at systemic velocities. So we don't have any outflowing gas that way. I'm certainly not opposed to it. The other possibility that people suggest for older stars is stripped stars, which would be an interesting contribution, which would require, kind of subsequent bursts of star formation such that we would have those older stars there. But other people have told me that, who study those objects, that you don't produce enough of them per starburst episode in such a low mass galaxy to get that much energy out. So I don't know, it still seems to be challenging, I guess.
Danielle, aren't the Wolf-Rayet lines much broader than the emission lines?
Yeah, so I mean, if we were in a Wolf-Rayet phase, yeah, we don't see any of the Wolf-Rayet features. The helium's incredibly narrow. We don't see any of the other characteristic features. But there's also, of course, this possibility that you had just a recent nitrogen enrichment from the Wolf-Rayet stars, and you're just past that phase. So you don't have, I don't know about I don't know.
And why is it that they don't form at low metallicity? I'm sorry, I'm
not a stellar expert, but I have been looking into this recently as I'm trying to study the stars more. So I don't know if anyone else wants to answer that, but I know that they are not
mass loss is too low.
Yeah. I guess. Yeah, a lot of winds require higher metallicies to drive the winds.
That's right. They're line-driven winds driven mostly by iron opacity. So if you don't have iron, you don't have winds.
So especially if you have extra low iron, right?
Are there other, yes, Mia?
Hi, thanks so much for a great talk. So I just had a quick clarification question. You mentioned when discussing the nebular emission lines that alpha enhancement might affect the hardness of the radiation field. I mostly do stellar spectroscopy, so I don't quite follow how that works in the ISM. How would alpha enhancement change that?
Yeah, so this is, I guess, along the lines of what we were just talking about. The idea is that the ISM is mostly dominated by the alpha elements, by the oxygen. So that controls the cooling within the ISM and what you see. But the stars, as we were just mentioning, the iron opacity is really important. And so with these lower abundances within these stellar atmospheres, it's metallicity dependent. And since it's dependent on the iron instead of the alpha elements, that's how that different in abundance can cause or can allow the radiation field to be harder.
I see. Okay, that makes sense. Thanks.
Let's see. Any other questions for Danielle? I guess I have a question about the nebular emission from, for example, carbon-4. I guess you can explain things well when there's no absorption at all. But have you tried modeling some kind of combination of emission and absorption for any of the profiles yet? Because I mean, it could be that you have that you're actually talking about emission coming from the very central region, and then you have absorption from gas that's outside of that central region that affects the appearance of the emission lines.
Yeah, so we did that that's what Max Patini suggested when I was studying that lensed galaxy with him and Don. So we did that in our 2018 paper for our lensed galaxy. Yeah, I haven't done it for all these new emitters yet, but for the two dwarf galaxies, the one obviously agrees with pure emission, and the other one, just from eyeballing it, yeah, it can be easily modeled just by adding a little bit of absorption. So I do think that that's all the things that I'm seeing from Don. Also just got Muse observations of those two dwarf galaxies. And so we also soon have a spatial paper coming out. It does seem that it is this very high central high ionization emission in these tiny galaxies, more of your standard H2 region thought. So yeah, Chuck, I think that's totally possible.
Thanks. Other questions? We have a few more minutes before we segue into the sort of chatting phase. Are there any other questions from anyone? I don't see hands up. All right, well, thank you, Danielle. What we're going to do now, how does this work, Monsi?
So we'll stay on the same Zoom connection, and there'll be a faculty meet and greet right after this. So thank you, everyone. And faculty, please stay on.